So good morning, everyone. I'm Razi. I was the lead last summer for the Comets computer engineering team at San Francisco State University. So our project was on developing a human-machine interface for gesture recognition using electromyography and inertial measurement unit data. So this is an overview of our human-machine interface, or HMI. The main goal was centered around creating an HMI that supports gesture recognition, and other goals included recognizing custom gestures and exploring different methods of pattern classification. So our sensory device was the Myo armband, which collects the data, and our C++ program, which takes care of the data processing. So the data processing involves feature vectors being fed into the trainer, which creates a model, and live feature vectors being fed into the predictor, which gives a gesture decision in real time. So before I dive into the technicalities of the project, I want to give a brief background on gesture recognition. So gesture recognition provides us humans a new medium to communicate with computers, and essentially we want the computer to have enough artificial intelligence to take commands just from our gestures. So a gesture can be classified as any movement from any part of the body, so like the head, face, hand, or arm. In our HMI, we specifically use the hands and the arm, and as I will explain later on. So gesture recognition can improve our daily lives and make it easier in many different ways. One way is making gaming more fun by offering us new controls, which may be more realistic. Gesture recognition can play a role in helping. Gesture recognition can help patients by playing a role in prosthetic limb control by making it more feasible. And since we're heading into an age of autonomous vehicles, gesture recognition can help control, in this case, an autonomous drone with simple hand gestures. So the sensory device was the Myo armband. It's worn on the forearm. It helps us collect both EMG and motion data. So the 8 EMG sensors wrapped around the arm basically detect electrical activity in our muscles from the surface. And the device live streams this data at 200 hertz. So after we have our raw data, we can apply feature extraction, which is a process used to reduce the dimensions of the input data and maximize gesture separability. So for the purposes of feature extraction, we segment the data into a fixed number of data points, which is the window length, and each window has a new set of data points equivalent to the window increment. So each window provides one feature vector, which provides eventually one gesture decision. So these are the different features that we use. These are known as the Hudgens time domain features. They include the mean, absolute value, waveform length, slope sign changes, and zero crossing. And these are some other potential features that we looked at but didn't implement. They involve complex equations and can, in some cases, involve additional processing steps. So after we have our feature vectors, the next step would be to apply a pattern recognition method to it. So over here we have two gestures, two sets of data points based on two features. So the question is, how is the computer going to be able to differentiate between these two? It's quite simply, it can draw a line. So if we have a new data point, it can, based on where it's plotted on this side or on this side, it will classify it as such. And if we add more gestures, it can get more complicated. So in this case, it would probably need two lines which are closer to each class. But we can always add more features and increase the dimension. So in this case, it's 3-dimension space. It may look more complex, but the data points vary more, which is good because a classifier can differentiate more easily and improve accuracy. So one of the classification methods that we investigated was the linear discriminant analysis. It's also known as Fisher LDA, and it's it's one of the common methods used to find a linear combination uh, of features that separates two or more classes. So over here we have two gestures based on two features, and it's projected onto this line over here. So on the left side it's mixed, but if we shift the line upward a little bit, we can get a better class separability and higher accuracy, which is what we want. So another classification method that we looked at was a support vector machine. It is able to use both linear and non-linear classification by using the kernel method. So it's loose. Some types of the SVM are based on applying kernel applications to Fisher LDA. So over here we have an input space with two gestures. So the Fisher LDA would have a hard time using linearity to differentiate between these two classes. So what we can do is, using the kernel method, we can convert this low dimension input space into a higher dimension feature space. So this way, the classifier can use a hyperplane to differentiate between the classes more easily. So we implemented two support vector classification methods and 4 kernels, so the linear, polynomial, radial, basis function, and sigmoid. So we tested the entire HMI with 6 people, 6 test subjects, and we recorded 6 gestures with 100 analysis windows. So the gestures were idle, fist, wave in, wave out, thumbs up, and point. So these are the numerical results. For the training data accuracy, we basically we recorded the data, generated a model, and tested the model again with the data it was generated with. So we expected 100% accuracy or close to it. For the testing, we basically took the entire data, split it in half, and created 2 models. And we tested one set of data with the opposite model. So this way the model was tested with a new set of data points to make it more realistic. So in our case, the linear kernel was the best, showed the highest accuracy. But these numbers can change kernel to kernel based on the situation. So if you add more gestures, or if you use a different feature set, or if you take more analysis windows, these numbers can vary. So our current human-machine interface is a basic list of features that it has. It has a user-friendly GUI. It can show data, show all these different features. So this is a screenshot, and this is the main input tab. Basically, it shows 2 miles connected. We also experimented with 2 miles. It has a playback feature, recording feature. And this tab basically shows the EMG data. These 8 channels are basically the 8 sensors that are showing raw data. We also have control for window increment and window length for the feature extraction. We also have a threshold because the 0 and turn feature make use of that. And we have this radar style chart to display all 8 channels and its features easily. You can easily see them at the same time. This is the classifier tab. Basically, we have the mean average value, which shows general level of activity. And we can choose a classifier and get lots of settings relating to it. So in conclusion, this HMI is a great research platform for testing out future newer classification methods and feature extraction methods. So in the future, we could probably experiment with 2 mile armbands and double from both arms and see if we can classify gestures from that. We can also use motion data to see if we can classify dynamic gestures. So after the internship, we had 16 interns who worked on 4 different projects, and they were asked about this program, and the overall result was positive. People learned a lot from all these activities. For me specifically, the activity that I liked most or learned most about was working as a part of a team. Being the lead for the computer engineering intern, I gained valuable management skills, and I gained valuable experience outside of an ideal classroom. So I was in charge of making sure the project progresses, and I learned a lot from that. Um, yeah, so I would recommend this program or anything similar to all community college students, especially those who want to transfer and are considering graduate school. So these are the sources for the pictures that I used, and that's the end of my presentation. Thank you. So the most difficult part was when we were doing this internship, basically one other team member and I were the only ones who had, well, others had programming experience, but since we were in charge of programming, Jeremy and I, we had taken one programming class. So getting all the data from the sensory, it was a lot of data, so we had to store that somehow, and it wasn't easy. We had to make sure it was stored and it was fast at the same time. So storing that huge chunk of data and then applying mathematical algorithms, it was a challenge to make sure everything was working. It's hard to tell if it was correct data too after it's just numbers, but is it like really the, what we want? Like you have to make sure it's working correctly. So that was for me. Oh yeah, so we used Visual Studios. So it's like for the Windows application. This looks like a generic Windows application too. So yeah, Visual Studios. Yeah, yeah. It was accurate. Yeah, yeah, it was accurate if you tried really hard for the gesture, but the boundary was a little shaky, a little fuzzy. So I think it could be improved definitely. So, oh yeah, so so before when I applied to UCLA, I was electrical engineering. And then after that, basically, I mean, I did a lot of programming in this, and I liked it. It was fun. It was easy eventually. So I actually switched to computer science. I thought it was easier, so it was more fun, more internship opportunities too. If you look at the website, people are looking for software engineers. Yeah, computer science and engineering. So it's, oh yeah. Oh right. Yeah. The counselors didn't. I could feel the counselors didn't like it because transfer students, you're supposed to be fixed in your major choice. But so I looked at the EE curriculum and compared it with other universities. So I basically went to the council. I'm like, I see, look at this EE class. It doesn't have enough programming experience, and we need programmers. Everything involves programming these days. So I applied to petition, and it was accepted. Um, I don't know what the percentage is exactly, but if you try, I mean, I think you can easily. Oh yeah, yeah. So they looked at my first quarter grades as well, and they told me second quarter. Yeah. Thank you.